Okay, this is problem 8-67C. It's on page 450. The built-up section shown in figure P867 is fastened together by passing two 3/8" rivets through the top and bottom plates into the flanges of the beam. Each rivet will withstand 2,650 pounds in shear. Determine the required spacing of the rivets along the length of the beam if it carries a shearing force of 125 kilonewtons. Now, I like this problem because it gives me a chance to show you what you should do when you're given both metric and English units. I know a lot of you don't like one or the other, and so you always try to convert to the system you like, and I'm trying to break you of that bad habit. But here's a problem where we've got both units in play. Now, do you think we should go for English units or should we go for metric units, and why?
English.
We've got a few votes for English. Okay, why English?
We already have two numbers that are in English.
Most of the stuff's English, so let's just go for English. That would be my, at this point, would I really care which one you used? Well, I would prefer that you use English because it'd be fewer conversions. Okay, so yeah, I would go for English units. In fact, that's one of the first things I did. I took the shear load that was given, which of course is a force, 175 kilonewtons, multiplied by a pound force per 4.448 newtons. And then, oh, by the way, I almost made the mistake you guys typically make on exams. I almost sat there and thought, okay, wait a second, I want kilonewtons here. How do I convert this? Which way do I need to move the decimal place? You can waste a lot of time trying to do stuff in your head. Here's the easy way. There's 1,000 newtons per 1 kilonewton. I know that's trivial, but it just avoids a mistake, right? It avoids a dumb mistake of flipping these two. So that way kilonewtons go away, newtons go away, and I know I've got pounds force and I don't have to concern myself anymore with it. Okay? So anyway, the load comes out to about 39,343.5 pounds force, which is, okay. So there's the shear load. All right, now also your author actually has a symbol. I don't know why he uses SD. I think S is for shear. D, I have no idea where that came from. I think it's, well, I do have an idea. I think it's across the diameter of a fastener, but I'm not sure about that. Anyway, this is the symbol he uses for how much shear load a fastener can take. Okay, so I'll just write it down in pounds force per rivet. Okay. Now, I went ahead again, I went into Excel and calculated the area properties, or the cross-sectional properties, the area moment of inertia, as well as capital Q. We'll check and make sure I got that right, but I think I actually did that one right. Let me write down what I've got, because of course we're going to need the shear flow. The shear flow will be dq over I. So we're going to need the area moment of inertia anyway. The total area moment of inertia came out to 831.3633 inches to the fourth. The average position, if you look at that figure, it should be on page 450. If you look at that figure, where do you think the centroid of that whole area is? In the center. Right, just in the middle. This is a symmetrical section. So it's just halfway up. How tall is that beam? Wide flange 14 by 43. Well, the 14 is how tall it is. So how tall is it? You'd think 14 inches. That's not the case. It's 13.7 inches. You actually have to go to the back of the book and look it up. Okay. So be careful when you're using these cross sections. The 14 is a nominal size. Okay, it's 14 inches nominally tall. What do you think the 43 stands for? That's how many pounds per foot it weighs. Okay, so it's kind of nice to know that that's the cross-sectional properties. Those are good to know. So all the standard sections are listed that way, where the first number is a particular dimension, and then the next number is the weight per foot. So 43 pounds per foot. Anyway, so to calculate the area moment of inertia, my whole point in that is that the center of that area is not half of 14 inches. Okay, it's different than that. Of course, I've got to add in the thickness of the bottom plate, but I did that here, so that should be the result. So there, anyway, so here's the centroid, here's the moment of inertia. I should write that down for the video. 7.35 inches is then the center of that beam. Okay, but what about Q? Well, to get capital Q, I need to calculate, I'll write it out on the board, even though I performed the calculations in Excel. That way we can make sure I did it all correct. Anyway, to get this, I need a particular area. What's the particular area? Well, here's the cross section. Here's the beam. I don't remember if it's a W section or an S section. But the particular area I'm interested in is this area. So I need the height from the centroid of the overall shape to the centroid of that particular area. Okay. The particular area is pretty easy to see, right? The particular area is just a 1/2 inch times 8 inches, so that's 4 square inches of area. But Y bar would be the distance from here up to here. So that's, let's see, if this is a 1/2 inch thick, then I should have half of 13.7. And then I have to add to that 1/4 of an inch. And I didn't do that right, so I'll have to modify my work here on the page as well as what I've got in Excel. All I did was I took half of 13.7 because I wasn't thinking right. Actually, I took half of the overall height and then subtracted 0.2. Wait a second, why 0.2? I've got a lot of things around here. This looks like the information from the last sheet. Did I not change this? I know what happened. I did my work on paper. Well, that's okay. So let's see, the total area of the particular area is 4 square inches because it's 8 inches wide and a 1/2 inch tall. And then the height to that, this would be the distance from the centroid up to here. I would need half of the height, so that would be 13.7 over 2 plus 0.25. You guys see why it's 0.25? Because that's half of this height. It's 1/4 inch. So then there's Q, or there's AY, which is Q. And I don't need that. Okay. And so then the shear flow should be the load, which was 39,345.5 pounds force, multiplied by Q. I didn't finish this off. We've got it in Excel. Let me jot it down for the sake of the video. That came out to 28.4. By the way, what are the units? Well, it's area times length, so it's inches cubed, right, or length cubed. Not a volume, but it is a length cube. So 28.4 cubic inches. Divided by I, but I was 831.3633 inches to the fourth. And let's see what we get. I'll plug this into Excel and let it do the math for us. So let's see, 39,343.5. And then multiplied by E12, that's Q, divided by H6, which is I, so that should come out right. So there's the shear flow. What are the units of the shear flow?
Yes, sir.
Not quite, almost. That cancels with all but one. So it's pounds per length, right? Or pounds per inch. It's pounds force per inch. Okay. Now, we really are not interested in the shear, so I'm going to eliminate that line in the spreadsheet. Save this before I forget it too. What we're really interested in is the maximum spacing. Excuse me. Well, we have to be careful here, yes.
Can we go over Q one more time, please?
Sure, which one? This one?
Yeah, big Q, yeah.
Okay. So see this particular area here?
Yeah,
That goes in right here.
okay,
You can see that's 4 square inches, right?
yeah,
Okay. Y is that distance.
okay.
I know that this is 13.7 inches. So I know this is 13.7 over 2. And I have to add to that,
Half
Quarter
of that
inch.
thickness.
right? Because this is a half an inch thick, I need half of that, so 0.25 plus 13.7 over 2, that was Y bar, and that came out to, whatever we had in the
Okay,
spreadsheet.
so
7.1.
AP is just the area of the top piece
Yeah.
that you have shaded.
Yeah, it's just the area beyond the axis where I'm interested in the shear flow.
All right, anything above that?
Everything above that.
Everything above that.
Yep. Good question. Any others? Did I do something wrong in the spreadsheet? Does it come out?
Yeah, I'm getting 29.4.
For Q, capital Q? Let's make sure I didn't make a mistake
I
here.
got the same thing you got.
Got 13.7 over 2 plus a quarter for Y.
13 divided by 2, 6.75.
Plus a quarter.
7.25 times 4.
I'm not sure where you mean 7.25. Is it okay? All right. I'm pretty sure we're okay at this point. So the shear flow came out to about 1344 pounds force per inch. Okay. Now what is that? Well, that's the load that each inch of length has to take. Now, how many fasteners are we going to put along the length? We're going to put 2 side by side, right? So we could think of this really as 2 times this, right? Because we're going to have 2 fasteners at each integral length. Does that make sense? Okay, however far we space them apart, really we're going to have 2 fasteners. Notice this is the amount of load that can be taken by each rivet. So this is per 2 rivets now. And we're going to put rivets side by side along the length. Okay? So when I calculate from equation 822, when I calculate the maximum spacing along the length of the beam, then I'm going to take really 2 times this. So let's see, let's just do this in the spreadsheet. Let's see, because the numbers I've got are slightly on. FSD. Oh, that's great. Let's try this. I guess a bad joke there was that's Greek to me. Okay, FSD. Okay, that really is 2650, and that's pounds force per rivet. And since we're going to have 2 rivets at each length S, well then the total spacing S, or the maximum spacing, would be 2 times FSD, I guess I don't really have to put the 2 in there, divided by Q, the shear flow. Okay? So let's see. So 2 times FSD divided by Q. So could we space them every 4 inches? 3.94 is the result. The number here is 3.94 some odd inches. Could we space them every 4 inches? Would that work? No, this is the maximum spacing. We have to have something less than that. So what would you recommend? 3.5. 3 3¾ I'd probably space them every 2 inches or more, or less, I mean. Does that make sense? Questions? Let me jot down the units here. This will just be inches. And really this is S max. So we could have an S specified. Just put really whatever we want. We could put 3 inches if we want. Okay. Anything else?